Pregúntale que ya puse ahí. Que sí.
Bueno, pues eso, voy a hacer la introducción. Su currículum y su doctorado de su grande, ¿no? De su.
¿Tienes internet? ¿Tienes internet? Internet.
Sí. Venga. Perfecto. Genial. Vamos a ver si entonces voy a inicio después de la presentación de Luis, será el primero.
¿Listo?
Bueno, un día, Alberto Cuellar. Nos temos uma vaca comendo bem morto. O professor Oscar Maurício Caicedo, fez doutorado no Brasil, na saúde, no Rio Grande do Sul, no Estado. E o momento mais menos o Luciano, fez doutorado na México, professor geral de São Paulo. Então, Luiz, tem aí uns 40 minutos.
Tá bom.
Para apresentar e apresentar a pergunta.
Então, bom dia. Eu vou fazer a apresentação em inglês. So, I'm gonna switch now. First than all, I want to say thank you to everyone for being here. Thanks to Luciano. He also was my qualification exam, so their comments will be really helpful in this time. Also, thanks for Oscar for accepting the invitation to be my bench, and also to my friends to being here supporting me. Okay, I'm gonna share the screen. Okay, as Christian was saying, I'm Luis Cuellar, Professor Christian, my advisor, and the idea today is to present my dissertation exam in order to obtain my degree, master degree. My work is called Network Function Virtualization Ontology towards a Semantic Service Implementation. The agenda for today's presentation: first, we are going to see an introduction, then a program review, the goals proposed for this work, a background needed to develop my proposal, then my first proposal, the implementation, and some use cases. Then we are going to see the second proposal, the implementation also, and finally, we are going to see the conclusions and future work. So, currently, service provider and network operator are having an appliance model in order to do service delivery of network services. So in this case, we have an end-to-end connection changing among them network functions, physical appliance and functions in order to deliver the service. So the idea of network function virtualization is to change the physical approach to a server-defined approach, where instead of having a physical appliance in order to have a network function, we are going to have a community of servers hosting the virtualized functions. In this case, a virtual machine represents the virtualized function, and in order to create the network services, we are going to interconnect the virtual functions. So the main components of NFV are the virtualized function itself, that as I was saying, is a virtualized function of the network. Then we have the infrastructure, is where the resources are in order to deploy the VNF, and we have an orchestrator, is the mechanism in charge of making the deployment of the virtualized functions. Here is the high-level architecture of NFV. In the right side for you, we have the orchestrator. In the left side, we have the VNF, the infrastructure, and also we have another component that is called the descriptor. The descriptors are just represent the behavior of the virtualized function of the network services in order to allow the orchestrator to deploy those services or those functions in the infrastructure. So the orchestrator takes the descriptor and deploy the VNF over the infrastructure. The infrastructure component has 3 layers. One layer that is our physical resources representing compute, storage, and networking, a virtualization layer in order to virtualize those resources. So this architecture is defined by the European Telecommunication Standard Institute in order to define the architecture, in order to define the components, and also in order to define the communication among those components. They also define interfaces to create the communication of the components. So now we are going to see the problem review. Here we have a deeper look of the architecture of NFV, where in the component side of the manual we have 3 additional components that are called the NFV orchestrator, that is the orchestrator itself. And we have a VNF manager that handles the behavior, the life cycle of the VNF, for example, when to initiate a VNF or when to terminate the VNF. Finally, we have a infrastructure manager in order to handle the resource allocation for those VNFs. So in this case, for example, when we are going to create an implementation of NFV in a local domain, what we have here, we have that maybe we can have different developers to develop each component of the architecture. We can have different technologies in order to create those components, different communication protocols, because the ETSI doesn't define anything of that. And also we can have different terminology to refer same components. For example, I was making an analogy. I can say hello, I can say hola, I can say oi. Those are 3 words for the same thing. So in this case, we can represent same thing, same meaning with different semantics. So in this case, how we can gain interoperability in order to communicate the components? We are having manual intervention. What we call manual intervention. Here we call manual intervention to the need of read manuals, read services, read metadata files in order to interpret and understand the capabilities of those functions, of those blocks, or of those components, also in order to use the capabilities. So in this case, we are going to use manual intervention to use the capabilities of one component in a same domain with the same definitions, or with the definitions already done by the ETSI. In an inter-domain scenario, let's say that we have solved the local domain issues. We have same developer, we have the same language in order to decode the elements, we have the same interfaces. Then we have 2 different implementations here. The first one are represented by orange color lines to represent the components. We have also a type of font called dry sans in order to represent the semantics, and we have also dotted lines, dotted gray lines to represent the interfaces. In the other hand, we have the implementation B representing the components, the gray lines. We have the interfaces represented by orange lines, and also we have the semantics with a different type of font. So in this case, for example, we have the same components of the architecture, but in different implementations. For example, if the manual wants to deploy or use maybe a DNF for another implementation, they may try to use the interface defined for that implementation. But such the implementation A doesn't understand the interface, doesn't understand the semantics, won't be able to use it. Maybe it can use also the descriptor defined for the implementation B, but also as the semantics are different, there are no, the implementation A is not going to be able to understand. Also, we can use the interfaces defined for them for the implementation itself, but same thing happened here. So how to get interoperability here? Once again, we're having manual integration. So the manual integration in this case, besides the things that we have for our local domain, we have another process that is build new blocks in order to integrate those components. For example, in order to integrate the domains. In this case, for example, we can create some components in order to parse semantics. For example, one descriptor has some semantics, and we implement a mechanism to parse those semantics into semantics defined for our domain. We can also parse requests. We can parse the interfaces. So in this case, the domain A is going to think that he's connected to the same interface. And also we can add some layers in order to understand different kind of interfaces. But the problem here is, in this case, we have 2 domains. But the problem is that we have 10 domains, 20 domains, any domains. The need of creating new parser, new mechanism of parsing is going to increase. So we cannot have, for example, 10 layers of parsing of parsers. Okay, so in this case, what we have here, we have that when the integration is more manual, we have higher cost of integration. If we go to a automatic path of integration, we can generate low cost of integration. In a summary, the problem we have here that NFV implementations are done without a common semantic, a common knowledge representation. We can also have that the descriptors of each implementation are done in an arbitrary way. We have inherent problems of mechanisms of integration mechanisms, in this case, the web services. That means that we have to do manual intervention in order to integrate the services, that we have implicit description of the services. We need to have a background in order to understand the service capabilities, and that's a higher cost of integration. So in order to do a research, we wonder which kind of common understanding, semantics, and communication mechanisms can be used on NFV implementation to reduce the manual intervention in order to obtain interoperability with automatic integration process. So in order to solve that question, we are going to get the following specific goals. First, the idea is to create a common representation of NFV domain. In this case, we are trying to create an ontology. Then we are trying to create some descriptors, some semantic descriptors based on the specification. Then we are trying to implement the ontology, that description, that semantic description created in order to create semantic services. Then we are trying to make an automatization of the integration process of services. And finally, we are trying to prove those integration process in a proof of concept. In the background, we have here the technologies used for the development of the proposals. In this case, we have REST services. The idea of using REST services is that each resource in the server side have an URI and a representation of that resource, and the client side is going to get some representation of that resource, is going to do some modifications to the representation, and then is going to update the representation in the server. This is done through the HTTP protocol and using a stateless type of connection. We have also the semantic web approach. The semantic web approach is done in order to change the current way of the web works today. Today, the web is meant to be for humans. So the idea is to, for example, in web semantic, to use a common language, for example, RDF, and use a representation of the real world in ontology. So in that case, the idea is to have explicit description of the web pages for the machines to understand, for the smart agents to understand those pages. We have the resource description framework. Is nothing else than a triple-based mechanism to express things of the real life. For example, we have subject, a predicate, and object. This, for example, we have to create a graph base of knowledge in order to create the explicit description. For example, for you people that are seeing the image, you don't know any context about this image. But if we start to reading the image using RDF, we can get a context in real time. For example, we know that Bob is a person that born in July that is interested in Mona Lisa, and the Mona Lisa was created by Leonardo da Vinci. So we start reading that graph and can understand some things related to the image. Then we have notation tree, a superset language to that graph model in order to create explicit description of the model in an implication language. For example, here we have two different types of ontology. The people are friend of a friend of ontology, and we have an implication. We have that Cindy knows John implies that John knows Cindy. So the idea also is for people to read and for machines to read and understand the context that we are having here. Then we have the ontology. What is an ontology? Ontology is something, a representation of the real life with the taxonomy and the components in the real life. For example, we have a domain in ontology. In our case, will be NFV, and we have a content, some abstracted things of the domain and the relations between them. We have the semantic web services. That is nothing else of making a join, making a cross of web semantic, a web services technology, where we pass from a syntactic and static level to a dynamic and semantic level. So we are going to pass from implicit description to explicit description of the service. In order to use web semantic technology, we have a REST desk. It's a mechanism in order to describe REST web services interfaces using notation tree language and also using if-then implications. Finally, we are going to use an inference engine. An inference engine is something that acts like a human. For example, we pass to the engine some rules, we pass to the engine some knowledge base, a knowledge base that is supposed to be created by a group of experts, and then the inference engine is going to make an inference process. Now, we are going to see my first proposal that was created, the ontology. How I create the ontology? First, we read the set of the specification of the ETSI. Then we make an abstraction of some sub-elements of the ontology, of the specification. We create the relationships among those components. We design a graph model, and then we implement that model using an ontology modeling tool. We start creating low-level elements of the ontology. What is a low-level element? A low-level element is the basic elements needed to deploy a BNF over an infrastructure. In this case, we take an information-based model based on the ETSI specification that contains which are the components that a BNF descriptor has to have. In this case, we have three elements. We took each column of this table in order to create some things of the ontology, of the abstract model. For example, you use the identifier to create the name of the element in the ontology. You use the type of the information base to create the type of the element in the ontology. Also, we said you use the same cardinality, sorry. And also, we use the descriptor field in order to make some relationships in order to understand the type of value that can have, for example, a property in the ontology, and then we make an abstraction here. We have two types of objects, two types of element in the ontology. That one is an object, the other one is a property or a slot. It's the same thing. An object is something, is an element composed by other elements. And a slot, a property, is just some feature of the object. Then we add, for example, here we add in the descriptor file, we put in the descriptor field, we put to which descriptor the object belongs. So in order to extend the model, for example, here we can see that in the video file, virtual device unit, we have that in the description field, that in order to see what a video is, we have to look into the clause 6.3.1.2. And when we model all the elements of the BNF descriptor, we go to the table and start to modeling the objects of that table. So we enhance our abstraction model and create new elements belonging to a different descriptor file. Then we start to creating some relationships among the components. As I was saying, a data property is something taken from a feature of the descriptor. For example, in this case, we have a property called ID that has cardinality 1 and has a value that the value of that property is a string. This is a feature because the property does not have any element related. So in the other case, we have a properties called object properties. That is in that case, to create the property, we have the verb has and the pointing to the object itself. For example, we have, I was telling the example with the video. So we have the verb has video, and the possible value for that property will be the object itself. Then we start creating a graph model. First, putting the object, the elements abstracted in the ontology. Then we start to put in the relationships and the cardinality. As I was saying, for example, in this case, we have a BNF descriptor that has a video component. Then we start to modeling the components of the video and start to enhancing our model. Then we start to create the high-level elements of the architecture of the ontology that are the high-level elements of the architecture itself, where we have the manager and orchestrator, the manu, the components related to them. And then here we make a merge between low-level and high-level elements in the descriptor class, because all the, as I was saying, the low-level elements on the things needed for the descriptor in order to deploy a BNF. I want to say here that we explore the reuse of other ontologies in our approach. In this case, we explore the use of infrastructure networking description language, INDL, but that model is used to describe resources. So we know that we can make a cross of the ontologies in the infrastructure part, but as it is out of the scope of this work, we don't do that much. Finally, we got our model. The model contains all the elements abstracted, the relationship, and the cardinality. We use that model to make the implementation using a Protege tool. First, we create all the classes in the modeling tool. Then the modeling tool gives us a XML file with the classes. For example, here we have that. For example, descriptor is a subclass of functional blocks. And that's a relationship created just by creating the classes. Then we start to modeling the properties. First, we model the data properties and the object properties. Then we model the data properties. When we have finished that modeling, we start to put in some facets to the properties. A facet can be defined as like a property of a property. In this case, for example, we have range and domain as facets. For example, in ID, we have that the range is the value that element can have in the ontology. In this case, is a string, and the domain is the classes that can use that property. Also, we have the cardinality. In this case, for example, for a BNF descriptor, we have that the property ID has exactly one element. Then the modeling tool give us the XML with the properties. We have the range and domain there, and the data and object properties. And I want to highlight here that, for example, in the case when for a feature for a property that is a string, we take as a reference another ontology that has defined the string value. Here is a complete definition of a class using the ontology. Finally, we make some use cases to prove our ontology. The test process was really simple. We took some descriptor files from current implementation of NFV and tried to parse those descriptions into using the elements of our ontology, and then we compare the original file with the semantic file. In this case, we express from a descriptor file to a semantic descriptor one. We have here, for example, the case of open button, where we have the elements defined in JSON, and then we pass the elements to using our ontology. I want to say here that the conclusion of this work is that for the implementation following the ETSI specification is really an easy process to do this parsing task. For the other thing, in the other hand, for a descriptor for implementation that does not follow the implementation, the specification, sorry, is not an easy task, and some elements cannot be parsed into using the ontology. Then the idea was to create some semantic NFV services. These services were created using none, the ontology previous created. So first we create, in order to create the services, we create first we create first web services, then we add some descriptions, some explicit description to those services using the ontology and other ontologies. Then we create a generic client in order to consume those semantic services. A generic client is a smart client. Finally, we create a proof of concept of the services. First, we create an open button web service that, and a client that, for example, the web service retrieves the file belonging to open button, the BNF descriptor file, based on some parameters that the client gives. So the client gives the parameters, and the web service retrieves the file. We have the parameters and we have the retrieved file. So we add the semantic description to the services, to the web service. Then we have the semantic NFV service. How a description for a semantic service, it looks like. We have, for example, preconditions, a process, and a postcondition. A precondition is some rules that has to be completed, that has to be achieved in order to make a process and to get a desired state. For example, we have, in this case, we can read this: if a BNFD file has an ID, has a descriptor version, if has a video, if has an image, then we can do an HTTP process with this get method, with this header, with this URI, a URI that is created dynamically based on the preconditions. And then if everything goes okay, we can have a postcondition that will be a BNF having a BNF descriptor. In order to consume those descriptions of those services, we create a generic client. Here was the core or the hardest work of this project, because what we have to do here, the generic client first pass the description and the BNF, the service descriptor and the BNF descriptor to an inference engine. The inference engine make a reasoning process and retrieves a workflow containing the request, the REST request, to be consumed by the client. So then the generic client reads that workflow and start to creating dynamically a REST request in order to consume the service. In this case, we have the URI and the method as a fixed parameters that all requests are going to have. Then we are adding some parameters with if and then implication. For example, if we have a header, if we have a response, if we have any parameter, then put that parameter into the request. After that, we create a dynamic client capable of adapt itself to create different kinds of requests to REST services. But however, we need something to integrate to make a service change of services and adapt the client in order to consume that service change. So in that case, we pass to the inference engine the service descriptor, the semantic file. Then the inference engine make a reasoning process and create a workflow of services in order to do something. That something is done because the inference engine makes some deduction and says, okay, with those inputs, I can do this. This is a process called forward reasoning process. I'm not using that. What I'm using is that we pass a goal, an objective to the inference engine to enforce a reasoning process to create a service plan of services to be consumed. In this case, we have the goal and we have all the services that has to be consumed in order to achieve that goal. In this case, we have that the goal is taken as a fact and then start to the inference engine start to see which service can be consumed in order to achieve that goal. So how the chaining process works. Some preconditions of one service can be the postcondition of another service. In that case, for example, when we have the goal, the postcondition of the service n is the goal. For example, the postcondition of the service n minus 1 is the service 1, and then we have the backwards reasoning chain. So how this works? We pass the data to the client, including, for example, in this case, a goal to obtain a metadata file. Then we pass the description to the reasoner, to the client. The client posts those inputs to the reasoner. The reasoner or the inference engine responds with the workflow. Then the generic client starts to making a process to process that file, then create a Java list of REST requests, make an inverse of the list in order to make a forward consuming of the services, and then consume the service itself. We prove that. We create a use case to do a benchmarking service, where we create several clients and several services that retrieve descriptor files for different NFV implementations. So in this case, in order to consume those services, developers or people have to create one client for each service. Instead of doing that, we create the services. We create the description of the services. We pass that a semantic file and the description of the services to the generic client. The generic client passes that to the inference engine, and the inference engine says, okay, with those inputs, we can consume, for example, the open button service. So he is going to do a benchmarking of which service is better to be consumed. In this case 2, in scenario 2, we have an automatic integration deployment process of open button. This, for example, in open button, to do a deployment of a BNF, we have to first manually create a BNF descriptor. Then we have to manually create a metadata file. Then we have to make a process in order to compress those files into a tar file. Then manually upload that file into the open button platform. In our case, what we did, we create the description. We use the facilities of the Intrix Lab, the cloud and the server. We create the services, as was saying, we create the descriptor. For example, we create a service to retrieve the descriptor file. We create a service retrieving the metadata file. We create also the description of the services defined in open button. That's some services that I didn't create, that those were the original ones. Then that's something that we can do, that the developers do one time. Then what the user has to do, the user has to create a semantic file, an objective or a goal in order to enforce a deployment process. For example, the client takes the inputs, passes to the inference engine retrieves the workflow, then the execution of the BNF is done, the deployment of the BNF is done. How it works is here. We have, as I was saying, the user create a semantic BNF descriptor and the goal, then pass to the client passes those inputs to the engine retrieves the workflow, the generic client processes that workflow, then decides how is the plan to consume the web services, Then he decides that he has to consume the BNFD service, BNF descriptor service. Then he knows that has to consume the metadata descriptor service. Then he has to create a package and automatically upload the, the virtualized function into the open button platform. Finally, I want to state the conclusion and future work that we have here. We have some conclusion that this work identifies some interoperability gaps that NFV implementation has. We try to reduce those gaps by implementing a data model known as NFV ontology. We also find that the projects based on the ETSI specification have a better chance to make work in an inter-domain scenario, also reducing the need of manual intervention. We have here that none open a window, a door, in order to implement semantic services in the NFV domain. Also with the use of an inference engine. We have that here we create a generic client capable of adapting itself in order to create dynamically web services, and also in order to consume a workflow of services. We found that the projects not following the ETSI certifications, that the current project of NFV are not following the ETSI certification. That's a limitation because when we attempt to do the parsing between the ontology and the original file, it's a problem. Also, we have that the current NFV implementation doesn't have any semantic technology. So our scope was limited just to do the semantic implementation in the interface. We also have that the implementation of non and semantic NFV services is just an initial step towards automatic integration. We create a proof of concept. We create automatic deployment process of BNS, but however, that's just the first step in order to create a automatic environment. Also, we have that the full potential of the ontology of the semantic technology is not fully explored. We make the generic client using basic Java technologies. We try to implement some semantic technologies as Jena, but they are limited by the inference engine. So there is no communication between the semantic technology and the inference engine. Finally, we have that the current state of the ontology does not fully fill all the needs that NFV implementation has. We need to create an enhancement of that ontology. We have to add some elements that are not included in the ontology, but are included in the semantic descriptor files that can be useful for the ontology. Finally, our contributions for this work, our main contributions was the ontology itself, often known, was also some descriptors with a semantic approach. We think as the introduction of semantic services in the NFV domain as a good contribution in order to create automatic integration. And finally, we create the generic client capable of reading, interpreting, and consuming dynamic workflows of REST requests. We want to make a statement here that current related works as NMDL, networking, modeling language, and the infrastructure modeling language just goes until the description of the components. They don't go further. They try to create interoperability in order to use a common language between domains, but in order to create that interoperability, they have to develop new blocks in order to understand the semantics. Our work goes a little bit beyond using the semantic services with the semantic technologies, and also we go a little bit further using creating the autonomous system that is called the generic client, that is maybe in the same field of machine learning for doing processes. Then we have, for example, a new part of autonomous system like Google is doing, like Uber is doing with the cars that are driving itself, creating context in runtime. Finally, we take as a future work, we think that we can create the components of the BNF implementation using the ontology. Also, I have the idea to put the inference engine into the orchestrator all in order to create automatic deployment or automatic consumption of the components. And that's all for today. Thanks. Siko? Tinha o relógio parado aqui. Agora vou detener a... Vou ligar para a Oscar.